field theory. Right. And you can explicitly construct Killing sphere on this space-time.
Can this temperature be lowered?
If you want, yes, I think you can lower the temperature.
And then what happens with black hole mass versus charge?
Let me see. I haven't think about it, so yeah, I'm not sure what happens. So you expect some phase transitions or?
No, I'm just. No. It sounds like you will violate the.
You something.
Oh
yeah, but as you lower temperature, I think mass also decreases or increases. Yeah, mass is a function of the temperature. So both degrees or decreases.
Both.
I think you can preserve this relation. Yeah. Okay, anyway, I skipped all of the detail, but so you can reproduce the Lorentzian limit. Lorentzian result. By the way, so this black hole was constructed by myself, and also I think I erased their name, Wang and Cho, and also Sujun Lee. Okay, let me summarize. Okay, my talk. Okay, so in my talk, I talked two things. Okay, one is renormalization group flow, and the other one is supersymmetry extension. So in the first part, I explained that entanglement entropy can be a measure of degrees of freedom in quantum field theories. I explicitly constructed a C function made of the entanglement entropy. So, but only in 2 dimensions and 3 dimensions. So it would be nice to extend such a construction to higher dimensions, especially in 4 and 5 would be very interesting. But nobody has worked out it so far. And also the second part, I talked about the supersymmetric extension of the running entropies. So I mentioned that we have to introduce background fields to preserve supersymmetries. So otherwise, you break every supersymmetry, unfortunately. So we modify the definition of the running entropy somehow, but you still take advantage of supersymmetries. So this is a new BPS observable. We should be, yeah, so I think we should be look into it in more detail. And interestingly, so all of the result of the super running entropy becomes the non-partial function. So the partial function on the known space. So there might be some extension of the super running entropies. But okay, anyway, so I'd like to stop my talk here. Thank you so much.
Can you consider, for the last point about superdrain entropy, can you consider the conformed field theory with a boundary, basically, system with a boundary?
Yeah, I think, yeah, you can consider such a system.
So the formula, the kind of definition you have still holds somehow. But you will be looking at medical with boundary now.
Okay, so one interesting direction would be that, okay, actually, so recently, so Omori-kun and Tatsuka-san proposed that, so usually to define entanglement entropy, you need to separate your Hilbert space into 2 parts.
Right.
But to consistently divide your Hilbert space, one way is to introduce a physical cutoff around the entanglement surface. So here I have region A, but and I consider some torus around this circle somehow. But the inside of the torus is no longer our theory. We ignore the degree of freedom inside this torus first. So this is the physical boundary.
Right.
And okay, in that case, the information at the entanglement surface is encoded into the boundary condition on this torus.
Right.
So, and actually, so you can map this space into the sphere, uncovered sphere, but you cut out the tip, right? So you have tau circle. But here you have some boundary condition at the tip. So in this way, I think you can compute the superlinear entropies with physical boundary. And depending on this boundary conditions, the value changes. So,
or even the conventional literature, a lot of time they consider, basically with the CFT only define on half space.
Half space. I haven't thought about it because, okay, in my case, I only focus on the spherical entanglement surface. So not planar case. So, yeah, it might be interesting to generate such a construction.
Connected with the recent program localization with the boundary as well.
Mm-hmm.
Well, okay, we can put it.
Any questions? For the superlinear entropy case, when you take n approaches 1, does it recover the Tatsuma formula?
In the gravity side?
I want to check if you add do the RT form.
Yes. Yes. Yes, you can recover the usual Ryu-Takanagi formula when n equals to 1. But Ryu-Takanagi formula does not work for linear entropies. Yeah, you know. No? Okay. There is no holographic linear entropy formula. Okay, Ryu-Takanagi formula works only for the entanglement entropy. There is no extension to the linear entropy.
Right.
But in this construction,
n goes to one limit, then you will get.
yeah, you recover Ryu-Takanagi formula.
I'm concerned whether this RT formula has been checked somehow.
So what do you check?
Check the duality between the field theory side and the gravitational side.
So I don't get your question correctly, but okay. I have to say that, okay, in a very simple case, so here I have a spherical entanglement surface. In this case, so you can map the boundary geometry to S1 times H d minus 1. And then we have a bulk geometry. And in this case, you can change the size of this S1. It depends on the size of n. So it depends on n. In this case, you can correctly compute the gravity action based on AD6 correspondence. I don't use any Ryu-Takanagi like formula here. I literally perform the AD6 correspondence. Okay. At least in this case, you can compute the linear entropy holographically by using such a geometry. But once you deform this sphere a little bit, then you can no longer use such a conformal transformations. And I don't know how to find such a gravity geometry. So there is no such a formula.
Okay, so let's thank.
Thank you.
We'll regroup at 3 o'clock. 4 o'clock.
Oh, sorry.